So good morning or good afternoon, everyone. And today, this webinar as a part of the TRB ABG 70 will host three speakers. And the speakers will provide us with a summary of their work for the shortlisted Kikuchi Karlaftis Best Paper Award of 2019. So that we had many excellent papers, and the committee they did excellent job shortlisting them for those three papers. So the first one, to keep it short, will be the paper called Artificial Intelligence Assisted Infrastructure Assessment using Mixed Reality. And we have the all three speakers are with us, Mr. Enes, Dr. Nishati, and Dr. Ulas. So if you go ahead and proceed, you have 20 minutes to present your work, and we'll keep it short for another 10 minutes Q&As. Try to stick to the schedule as some people are joining from overseas. Thank you, and good luck.
Thank you. We really appreciate that. This is Necati Çatbaş. I'm a professor at the Civil Environmental and Construction Engineering Department. First of all, I would like to thank again the committee for choosing our paper as one of the finalists for this award. And this is an interdisciplinary paper, and the other senior author, Dr. Ulaş Bağcı, is also here.
Hello, everyone. We are happy to be here, and so yeah, hopefully it's gonna be a shared success for all the community.
And the person who really did most of the work is our student, Mr. Enes Karaslan. He will be presenting the work, and at the end, he and us will be here to address any questions that you might have. Yes,
thank you very much. Good afternoon. Today I'll be introducing a very new approach for visual infrastructure inspections. We are using the artificial intelligence to assist the human inspectors through the mixed reality system. I work together in this project with my PhD advisor, Dr. Çatbaş, also Dr. Ulaş Bağcı, who is a computer science professor and the director of the Computer Vision Lab at UCF. To provide a brief outline of the presentation, I will first describe the problem in the visual infrastructure inspections, then explain a novel solution that we brought together using artificial intelligence and mixed reality. And then I discuss the technical part of our methodology in very detail. Lastly, I will show a short demonstration in a real-world application. Before we conclude our presentation, we will provide some remarks and accept your questions. To our best knowledge, I think this paper is the first approach to integrate the AI with mixed reality for infrastructure inspections. It's also the first example of real-time collaboration between the AI and the human inspector. With human supervision during the process, the methodology introduces a trustable AI for high-risk applications such as bridge inspections. Our methodology also provides a true attention guide mechanism as opposed to the other attention guide approaches in deep learning approaches, the applications. The human always verifies the region of interest in our methodology. As Dr. Çatbaş indicated, this is a highly interdisciplinary research work. We collaborated with different departments at the university. It's a combination of structural health monitoring, data science, computer vision, simulation, and training. So can human inspector and the AI collaborate? The conventional techniques of visual inspections have innately large subjectivity due to many reasons. Varied experience of the inspection personnel, overconfidence on the historical inspection data, even the difference of methods used for defect measurement. Most of the time, there is only qualitative assessment for a crack or spall instead of a quantitative measurement. because measuring every single crack or spall on a concrete structure will be very much time-taking. There are recent robotic techniques, of course, came into practice, which benefit the power of AI to analyze these defects automatically. Yet these techniques still rely on the inspection engineer's professional judgment. Then we ask this question, can human inspector and the AI collaborate instead of replacing the human in the process? Can we create a collective intelligence? Our approach in this paper is to use mixed reality as an environment to facilitate this human AI communication. I think the audience is probably very familiar with the mixed reality, but I will go over quickly what augmented reality, virtual reality, and mixed reality is. Virtual reality is a computer simulated reality. It replaces the physical world with completely virtual environment. Augmented reality, on the other hand, generates content onto the physical world. Mixed reality, MR, is now the new thing in which real and virtual objects interact with each other.
Right now it's happening.
In real time.
One is going on. So this is not interesting.
Can the audience hear
This paper was
speaker
I don't know which year.
and the mute?
I ask people to put their mic off.
This is live? Yeah, this is going on. This one, yeah, this one. See, there is 3 webinars. Artificial intelligence assisted infrastructure. That is what is going on.
We can hear you.
There is
We
GPS
cannot present it.
based traffic congestion prediction using.
Dr. Zek.
Yes.
Dr. Zek.
Okay, that's good.
Excuse me?
I think
Can you please stop talking while the talk is on?
Speaking, and we hear them. We cannot present.
Yeah, please put your mic on mute, please. Sorry for that. Go, Dr. Bishop.
Okay, thank you very much. I'll continue and keep up our timeline very quickly. So I was explaining what AR, VR, and the MR is briefly. Mixed reality is the new reality that the virtual and the real objects interact with each other. This figure here is called the virtuality spectrum. The immersive and holographic devices are in between these AR and VR. So how do you build human-centric AI, which maintains the human connection and understands the limitation of technology to leverage a human-synthetic partnership? In our approach, the AI accelerates the certain task of the human inspector, but also asks for input from the user to verify itself and improve its accuracy over time. The inspector can always intervene in the process, provide a professional judgment. Mixed reality, we think, is an ideal platform to build this kind of interactive collaboration. This is an example human-centric approach from our AI system. Here, the inspector looks at a bridge girder. On the left image, the AI could not detect one of the spall regions when the prediction threshold is set to default value of 0.85. On the right image, as you see, the inspector lowers this threshold just a little bit, and the AI instantly detects the other spall as well and automatically analyzes the quantified area. Training a deep learning model can be very challenging, especially if you have very limited amount of data. You may easily face overfitting problem or end up with not really generalized behavior. In this study, we first gathered the images from publicly available datasets published by other scientists. We eliminated their bad samples, unified their annotation styles. Then we added on top of it our own dataset, which had good quality samples, but less in number. As a last step, I applied extensive data augmentation, and if applied properly, data augmentation can considerably improve the model performance. I applied here some rotation up to 90 degrees, translation up to 30 pixels, horizontal and vertical flip, scaling, cropping, and some noise. Convolutional neural network is a deep learning model that works very well with image data. The CNN models are typically composed of convolutional activation and pooling layers. This is a very commonly used architecture called AlexNet, and the novel architectures are actually inspired from this model. For damage detection, I use SSD-like MobileNet v2. For damage segmentation, I use the modified SegNet. We essentially use the SegNet model, slightly modified for our purpose to run it faster on the mobile devices. The convolutional layers simply extracts features from the images, and in the activation, you decide if a neuron should be activated or not. And the last pooling layers, you downsample all the features and create a feature map. Training a deep learning model requires high amount of computational resource because you're simply iterating millions of parameters using multidimensional matrix operations. I use, in our study, UCF supercomputer Newton visualization cluster. It has 10 compute nodes, and in each node, there are 32 cores with 192 gigabyte memory, and also 2 NVIDIA GPUs. If you train 800,000 steps, meaning that if you feed 800,000 times batches of images, it takes about only 18 hours to train. On the other hand, our models can run on mobile chipsets in real-time speed. The minimum required hardware configuration is 4 gigabyte RAM, a Pascal GPU, and a mobile CPU. We first tested the robustness of the detection model in some challenging scenarios, and the results are very promising. On the left image, a spall region was detected from a long distance with very high confidence score. On the right, a vertical crack on the wall was detected from an angle, large angle, also with very good accuracy. The detection model, even though the scores are very high, the detection model doesn't have to perform always at high accuracy in our approach, because we implemented a semi-supervised approach in which the inspector can easily correct the bounding box if a damaged region was not detected properly. The AI system will learn from these alterations and gradually improve itself. To be able to quantify damage, it's not solely enough to detect the damage in a bounding box. The damaged region also needs to be quantified so that the condition of the defect can be calculated. Therefore, there is another AI model we put into operation that works sequentially with the damage detector. This model performs only segmentation, namely the quantification of the defect. There are very powerful segmentation architectures, and we use a model named SegNet here. We slightly modified the model architecture, reduced the number of convolutional blocks so that it can provide better inference speed on the mobile device. So these segmentation models are very successful in the medical imaging. They are trying to segment cancer lesions from the healthy tissues, and here we are trying to subtract the damaged regions from the intact concrete. So there is an interesting similarity between human health monitoring and structural health monitoring. We use one of, and in our model, we also use a technique called attention guide. In attention guide approach, essentially the damage detector provides a region of interest for the segmentation pipeline. Therefore, our model produces 30% more accurate results in quantifying the damage than using just the segmentation. This is how attention-guided segmentation works. On the left, the entire image without an attention guide was input in the segmentation model, And as you see, there are regions that show up as damage, but actually irrelevant things. Some misclassifications will appear. But when I input only the detected region inside the bounding box, SegNet quantifies the damage at much better accuracy. And as you see, all the misclassified pixels are removed. These are some real-world results where the human AI and collaborated to both detect and segment the regions, defect regions. Okay, we will ultimately need real dimensions of cracks or area of spots for condition assessment. It's not solely enough to quantify on a 2D plane. So we needed to project the 2D result onto 3D plane. To be able to do that, the first thing was to calibrate the headset's camera with the inspector's eyes. Luckily, these headset manufacturers provide camera eye calibration tools, and that makes this process very easy. After the cameras are calibrated, now I can estimate the dimensional properties at a much higher accuracy. The 3D projection essentially uses 3D computer vision techniques, which are matrix operations in projective geometry instead of classic traditional Euclidean geometry. A dot, for example, corresponds to a ray. A plane means a conic in the projective geometry. The main operation here is the 3D transformation. The image is multiplied by this projection matrix, and we ultimately obtain the 3D projected result. Lastly, when we estimate the dimensional properties, we can now estimate the condition of this defect. We implemented here an example condition limit state criteria, but other breach guidelines can be easily integrated in our system, such as AASHTO, NBIS, or local DOT guidelines can be easily used. I will now show a very quick real-world demonstration that we did in a real breach site. My friend Kevin helped me at this breach site to perform an inspection here. We use a mixed reality headset called Magic Leap, as you see here. We integrated our models, created a simple user interface to facilitate the human AI collaboration. In the headset interface, you will see it now. When you click on the scan button, the damage detection model will locate the defect in a bounding box, and it will place a confidence score for this bounding box. After verifying the attention region, you will click on the Analyze to run the segmentation model. The segmentation also has a confidence threshold for pixel-wise classification. As you see here, the 3D projection in mixed reality show the analysis results at correct location from different angles and distances. I move my head around and it's still at the same location. To obtain a more accurate defect quantification, I can simply adjust here the segmentation threshold. I did it, I lowered it here to 0.55. And when I run the analysis again, now I have much finer segmentation region, as shown in the red colored area. Now I will do the same process for spoles. I determine a large spole area here. The model first detected, put it in a bounding box. When I use a high threshold value, I see that some of the regions were not subtracted accurately. So I reduced the threshold value, and now I will get almost a perfect result for damage segmentation. So this is an example human AI collaboration when we benefit from the power of artificial, artificial intelligence. Lastly, I would like to provide some concluding remarks. Our novel approach here, the attention guide mechanism, provides 30% more accurate defect quantification than using a traditional segmentation approach. And it provides near real-time execution with the lightweight models we develop. And we did a lot of speed optimization to run it faster on the mobile devices. We implemented a human AI collaborative framework for reliable functional practice, inspection practices. And these deployed headsets, these holographic headsets, have useful additional features such as remote expert communication or easy integration with infrastructure asset management, decision support systems such as H2AR BRM. Nowadays, the recent headsets are very lightweight and have unique designs adapted for field work, such as hard head attachments you see here. And now the industry basically proceeds toward the construction and maintenance practice. Thank you very much again. This is our contact information. You can reach us anytime or email us. And we can accept your questions if you have any.
Thank you very much, Dr. Shadbas and Dr. Parchi. I will start. Any question? I guess everybody's muted, so make sure if you'd like to ask a question, your mic is unmuted. Go ahead.
I have a question. This is Osama, the University of Tennessee. So how long does it take for this algorithm or for this app that you developed to do all this analysis that you just showed in the video? Like from the moment you spot some spall or whatever until the moment you get or analyze it?
So when we started this project, the main challenge was to be able to integrate the AI in mixed reality, because the mixed reality didn't have enough hardware resources to be able to execute the models that we develop here. And in terms of technical wise, it was really hard to implement. Nowadays, the most recent headsets come with native AI support, so it's much easier. But it took a lot of time to find a way to integrate the AI and also the mixed reality platform and work together. And another challenge, so this was an iterative process. The entire project almost took two years. We deployed some models, didn't get enough results, so we retrained our models with more data set, perform more data augmentation, and now we get much better real-world results and much more generalized behavior. But as I mentioned in my presentation, the model needs to be used more in real breach inspections, because we created a system that that the AI will improve over time gradually.
I guess my question is what's the processing time like when you go to the field and you want to analyze it?
Inspection practice, or
on the you mean on the field?
In the field?
Yeah, in the field, when you're in the field and you're trying to analyze some
the responsiveness of the model, that basically whenever you track the crack, how long it takes for your model to detect it.
Exactly.
So,
Maybe from
the performs almost near real time. So you, in the user interface we created, it was just for simplicity, but you don't really need to click a button or something. So it will run in the background, these models near real time. Very quick, with one click, and very short, after short time, it will analyze the defect region and show you the output.
Perfect. Thank you so much.
Any other questions from the audience? I have a question. So given that you're now able to, I guess, what we call classify the cracks, right? We can call it classification, if, right? can we know the severity of those cracks? Can we know how we look at one type of crack, but we know how bad is this crack for the infrastructure? And,
yes, we also implemented, for example, here in this example, I further classified the crack types, such as line crack. You see some lower confidence score here. It's only because the classification score is multiplied again, a further classification score. So we first classify whether this is a spall region or crack region or not. Then we classify further to know if it's a line crack or alligator crack or other type of crack.
But how about the damage level? Can you identify that as well?
Yes. So here in the mixed reality 3D projection and the stereo imaging capability of these headsets, we can estimate the distances very accurately. And when we can simply apply the condition limit criteria in different inspection manuals. We use here, since it's an early work, we use an early version of ESHTO as an example, but it can be any inspection manual, can be integrated in the system, local DOT's guide or NBIS.
Can I ask one last question?
we still have time, I guess.
Yeah, this is Sam again. This is really a very interesting work, so it's triggering a lot of questions for me here. So why are you considering this mixed reality and not augmented reality, given that you're not really controlling that, you know, like that focus area, like in this image, that green box? Are you able to control it, increase the size of that box?
Yes, that's the human AI collaboration. If the human doesn't think that the bounding box is not correct, it can very quickly, very roughly correct it. Just pull the bounding box to a different size. Now you have a different attention region for your segmentation and your model. So this human process in the middle is the novelty in our approach. We verify the results during the process.
And you change that area using buttons in the app, or?
There's a controller. Basically, it's a very easy to use controller. You simply, the new headsets doesn't even need controller. They use it with hand gestures. So we can use your hand gesture to enlarge it or make it small.
What is this headset again?
This is HoloLens 2. They adapted their designs for hard head attachment. It's now published. It's by I think introduced by Trimble, a company works for Microsoft.
Yeah, amazing. All right. Thank you very much. Thank you.
Thank you, Dr. Lars, and thank you, Dr. Nishati. So before wrapping up this, I'll just forget to mention that the presentation will be recorded for the ABG 70, so other members can enjoy this work and can benefit from this work. If you have any questions, you can ask. So last thing, so what we're going to do now is we're going to transition to the next talk. So I will ask the next presenter to start sharing their screen. And I would like to thank the first presenter for this really, really great work. Thank you very much.
Okay. Thank you very much again.
Thank you.
So next is Dr. Kenyon, right?
Can you guys hear from me?
Yes.
Let me try to share my screen. You guys see it?
Yes.
Okay, great.
So
should I start it?
Yes, definitely. I will just introduce you. So basically, the title is here. It's the second paper in our seminar, and we have Kenyon from ACOM will be presenting on behalf of his colleagues. Go ahead.
Thank you very much. It's a great honor for us to be invited for this presentation, to be a shortlist for this award. Actually, this piece of work, I'm participating with other authors from China, professor from Tongji University, another professor from Zhejiang University. Actually, my name's Qin Yang. I'm working for a corporate called AECOM in transportation industry. So the paper we try to present here is, as the title mentions, how to use the GPS-based traffic data to predict the congestion. And we use innovation neural network modeling, try to make the work more productive and more efficient. So the content I'm trying to present here lists as this slide. A little bit brief, talk about the challenges to do the traffic congestion prediction, and a little bit overview on the machine learning, deep learning approaches, and compare with the traditional methodologies. And mostly we'll talk about the innovation in this research paper, and there's two highlight points. One is regarding the how to interrupt the data and use the data sources. And second one is how to construct neural network modeling to make the work more productive. And the last portion will present our result for short-term and long-term prediction performance. So as we know, the traffic congestion is a kind of really interest topics in widely community, not only for the common travelers, but also for the traffic management agencies, which is all care about. But if there's a way which can help us to have advanced prediction on the congestion level at a certain network, that'll be great for either for example, for the regular travelers. It can give you the very good information for your prepare your trip, or in the middle of your trip, you will know the status of the traffic. And also for public agencies, it will help you run a lot of your programs, for example, for help you identify the congestions and find a way to reducing the congestion and doing incident management. So, and on the other side, traffic congestion was impacted by a lot of factors, as we know. It's a complex issues, which could come from the infrastructure side, like the road geometry and capacity, and the traffic demand changes, and traffic flow complexity, and also the weather conditions. The construction and special event also impact the traffic congestion. That's why there's no universal single model which you can running very well to predict what happens in the next moment for the congestion status. And therefore, it's a very hard topic at the research side to find a way to actually doing the prediction as much as we could. There's a lot of researchers for the past, I would like to see more than a decade, try to solve these issues. Traditionally, there was a lot of researchers focused on the model, we call model-driven methodology, which use mathematical tools such as statistics tools, which can help you actually running some kind of construct some model and try to use the data help to do the prediction. There's some limitations for this. One is all the mathematical models based on really strict hypothesis. And sometimes it's hard to combine both the spatial and temporal information all together to get the better result. And also, as we know, that's a hot topic in this committee, which is the data-driven method, especially the machine learning method that was developed for the many years up to now, And there's been a lot of successful stories in other areas, for example, imaging process, video process, all that, which also been penetrated in the traffic prediction area. And there's a lot of research as well in this area. As we doing the literature review, we look at that, and mostly was concentrated on small-scale network. And the other side is the traditional neural network architecture, which is focused more on the hidden layers in the middle, and give some limitation before we go to the deep learning area. So with that, and give us ideas with a lot of success on deep learning, we could do something on this area. In addition, for the data sources, there's also a migration as well. Traditionally, we use loop detectors, we use video detection and radar detection to collect the data. But now we have a more wide area detection method, which is a proof data, which is gathering from GPS-based vehicle trajectory data. And compared with traditional detection, and this GPS-based visual trajectory data have the advance, at least on the first one, is easy to be collected in real time. And the second is can get it at a large coverage instead of some pinpoint at the road network. So with the thought on this, we try to explore our idea more, and we try to assembling together with our approach to solve the problem. From the algorithm standpoint, there's a lot of advance, as I just mentioned, success in other areas, which we look around and the following interesting work about a neural network we think we can take advantage of. And one of that is called a convolution neural network, which has been approved is very good at perform to capture the special features. And the second is called a recurrent neural network, and which is has been approved, but very good at capturing temporal relations. And in particularly, there's a lot of models being proposed. And for example, a very famous one called long short-term memory model. As a version of that is called gated recurrent unit model. They are very successful in other fields, but in this area of the traffic status prediction, we'll try to assembling this together. So in terms of data, as a lot of previous study also explore on this area. So mostly the speed data is the most majorly being used, but we saw that's probably not enough. We can incorporate more data, go beyond the speed. And a lot of previous research need the demand to make a priority of knowledge for the GIS, which is construct the basic of the road network and build the algorithm based on that. And there are also issues for neural network itself, which is called management exploding or grading. So with that, we kind of explore our research and try assembling all these issues and ideas together. And we saw the new opportunity as at the data source point, we tried not only use speed, we also use the acceleration information combined together to get better performance. And the other side, we tried to use a three-dimension convolution network, which is not only considered XY, which is a geography coordination, but also consider the timing changes, which is the other D, combined together as a 3D. And we propose as a hybrid solution with this. So with such, I want to mention here the major contribution for this paper. First one, we proposed a brand new hybrid deep learning network. And we use the second, we use the vehicle trajectory data, which produce both the speed acceleration for the measurement. And as a last portion of the research, we compare this proposed methodology with some existing algorithm together to see, compare their performance. So this is the whole architecture diagram for this hybrid neural network. As you can see, the data being pre-processed as going through a two-channel. We call one is a combination of the 2D convolution network and RNN together. The other channel, the 3D convolution network, and then they merge together as a whole solution. And all this actually to be used to process both the speed and the acceleration data, and combine those data results together to produce the congestion level. So some details about the algorithm. I wouldn't go much on these formulas. It's all in the paper. So basically, the procedure we're taking is, as the diagrams shown, is a mesh network which represent the XY, which is coordination, and another dimension, which is the time. Basically, we take the algorithm actual original from the video process. We using the grid network, which is each grid approximately 100 meter, multiplied by 100 meter. We average the speed and the acceleration based on this grid for all the sample data we got. And we also do the normalization for the data. And with one channel, which is we use the 2D CNN network in junction with the gated recurrent neural network together. This is the other process algorithm. So for the 2D CNN, we use 3 layers combined with the subsample layers in the middle, and the 4 connection layers by the end. And gated recurrent network, the reason I would like to mention that reason we use this, and by not using the long short-term algorithm, is because this is kind of very simple and a very straightforward and more efficient algorithm. This one, LSTM, actually, you can see normally have a 4 gated to be adjusted, and this one only have 2, which is very easy to manipulate it and have a very efficient way to do that. So regarding the 3D algorithm, as I mentioned here, this is the first time actually as to use the 3D neural network model to do the traffic prediction here. So we also use the 3 layers of a convolution neural network, and with the subsample layer in between, and finally get the 4 connection layer to produce this the whole data to the whole result together. This is kind of compare the 2D CNN with the 3D CNN together, because the 2D, you can only handle the XY, which is great, but we have to use other algorithms. For example, we use RNN to produce the time changes and to get the result. So this is, again, this is the whole algorithm architecture. With the data set, we use the data from the vehicle trajectory, in particular area, which is in a city called Shenzhen in the southern China. And it's a large urban area, which is roughly 2,000 square kilometers, with a population as 12 million there. And as the purple area shown in this map, which is called the Futin area, is we use the data, which is a GPS sample from there, and it was aggregated, pre-processed data set. And this is the computing environmental we are using, basically, and the data set we are using. Basically, we gather data for like 21 days as roughly 3 TB database. And we divided it by 2 sub-data sets. And first 20 days we use for the training, and the last date we use to testing the performance of the model. And by the way, the data we collected with the estimation roughly represent the 10% of penetration rate for the whole traffic network. As the congestion, we are going to produce the result. We define the congestion based on the speed and acceleration rules together to get the congestion level. As you can see here, we define the mild congestion if your speed is less than 20 kilometers per hour and your acceleration is still bigger than 3 meters per square second. So, and the other rules for accelerated congestion. So in terms of running the model, we use the simple workstation and also take advantage of the GPU capability. And we use the wider, in particular software called the Compute Unified Device Architecture to enhance the calculation. To measure the performance of the algorithm, and this is the specification we're using to do that. And one is use the root mean square errors, the accuracy of the data result we got, and the recall data we got. If we can see the RMSE is this lower the best, and the accuracy and recall the higher the best. This is the short-term result. We're using the 5 minutes aggregation data, try to produce, predict the advance in 10 minutes, 5 minutes, 10 minutes, and 15 minutes. We call it's a short term. We also compared with the other algorithm in here, the 3D convolution, the CNN-RN hybrid network, and a gated recurrent unit network. So you can see I highlight here the green portion, the errors we got, accuracy of algorithm is outperformed than other algorithm. And because we're using hybrid model, one thing I would like to point out, the training time is kind of much longer compared with the other algorithms. So this is a summary of the short-term prediction result. As I just mentioned, this is a predict 5 minutes, 10 minutes, and 15 minutes with our 5 minutes data, and we compare that with other models. And there's a details calculation for the how the increase of the accuracy and the recall of our algorithm compared with others there. And we also run called the long-term prediction result, which we're using our data to predict next 30 minutes, 35 minutes, and 40 minutes congestion level. And as the same result as before, I would like to point out a couple of, one is the longer term prediction result compared with short term is kind of the errors getting bigger and accuracy and recall getting lower. But still compared with the other algorithms, and our result is still our algorithm still give the best result. And again, the training time is kind of longer than others. And here's present the result of that. In particularly, we look at the root mean square error for different algorithm as well. Algorithm, by the way, we give the name called CRC3D. Compare with the 3D convolution algorithm, which is called C3D, and CNN-RN model, and also RN model, gated recurrent unit model as well. As you can see, the yellow line is the hybrid model we propose is perform much better than other models. So the left side is for the short-term prediction, and the right side for the long-term prediction, and this is for the speed data. And this is for the acceleration data. Still, it's produced a similar result as that. As a wrap-up, as a conclusion, this paper is kind of proposed innovative hybrid deep learning neural net model, try to solve the congestion prediction issues. As three highlight point, and one is we kind of try to use more data, go beyond the traditional speed data. We use speed and acceleration together. Second one, we use the integration hybrid model, not only use the CNN-RNN model, but also parallelly we use the 3D convolution model, which is we thought is first work to use this type of model for track flow research. And other highlight point is that we try to use this algorithm to predict the larger scale of the congestion status, and the area actually we collect the data. It's just like 36 kilometers by 25 kilometers. So compare with the other models, this is data. Actually, this model gave us very good, the best perform compared with others. So one thing I think desire continuous research and on that is like our training time of VS is longer than others, which is another point down the path to be improved further. I think that's all concludes my presentation, and here list all the answers for the paper. And appreciate if you guys have any more questions. I try to do my best to answer them. Thank you.
Thank you, Ken, very much for this interesting talk. So we have around 9 minutes for questions. Any question?
Hello, can I have a question? A quick question. This is Ulash from UCF.
Hello.
Hi. It was a great talk. Thank you very much. I have two very quick questions to clarify.
Mm-hmm.
I'm trying to understand one thing. You said you are using CNN, RNN together. Is it the convolutional LSTM you are using because that works the same way? Or you are meaning something else by CNN, RNN?
Yeah, it's a convolution network because let's go back to this quick algorithms. Let's see. We use together because traditional CNN mostly being used is a 2D CNN network.
Yes, I understand that actually. So
yes.
What I was asking is it the convolutional LSTM is a specific network?
No, it's a convolution. It's convolution neural network, yes.
Okay, so the second question, when you are using, you said that you are combining CNN and RNN.
Yes.
I guess you are doing the decision fusion. Am I right?
Yes.
Okay, thank you.
So this is Mehdi from Department of Transportation. May you go back to your objective slide if you have any? I still try to find what do you want to achieve here?
Basically, we're trying to use the new data sources to predict the congestion status directly, because the normal way to do that is kind of you create a very complex model. You feed in the data, for example, in the speed or volume, occupancy, those data, and you set up threshold, and then you come with congestion network. The reason we use this machine learning is because you know machine learning had a very good advantage to solve the nonlinear issues, nonlinear problems, which if you're training well, and it will feed in the data immediately, give you the answers you wanted. So we feed in the vehicle trajectory data. We want to get the congestion status directly.
So Where is the prediction? Basically, you are saying that you're going to predict the congestion, and I don't see any specific result.
We
supporting
basically use the 5 minutes aggregated the vehicle trajectory data. If you look at the model, basically for each of this grid, either the black or whatever the color is, within each grid, we average all the vehicle data samples within this grid with the speed and acceleration. Those are the basic data set we got. And when this data fit into this neural network model, let me go to here, and from the left, and the right is we give you the directly congestion level, and the methodology to rank if the congestion or not. The output data will give us, for example, you predict the next 5 minutes or next 15 minutes at this grid, how the speed is going to be at what range, and your acceleration at what range. Based on this, the right side of the rule will predict, okay, after 5 minutes, if this grid is going to be congestion, it's going to be non-congestion, it could be zero congestion. So that's the result we want to get.
Okay, thank you.
I have a question. This is Osama, University of Tennessee, Chattanooga. So you're trying to predict congestion level, not congestion locations? Locations?
Well, this is the congestion. Actually, I would like to mention. So this algorithm kind of a little bit different from the people see. For example, the traditional way you talk about congestion on this road segment, right? But this is a congestion prediction is fit into larger scale. For example, city air, and okay, that air give you mostly the microwave, not microwave, but macrowave level of the view of the whole city network can be congested. So it's not give you an individual road segment if it's congested or not.
So it tells you whether the entire network is congested or not?
Yeah, yeah, at what portion of that is going to be congested.
So what portion of the network is going to be congested? And this is, yeah, so this is the division, the 100 by 100 meters that you did.
Right, that's correct.
Got it, got it. So if you please go back to the results slide, the long-term prediction slides.
Okay. Sorry, it's in the back. This is the longer term.
All right, so your algorithm is the second one, and right?
Yes, yes.
And it seems to me to be very comparable, like producing very comparable results to the last model.
Yes, yes. You asked a very good question. We did realize that the 3D convolution networks have a very good performed network, and why we still use the parallel level of architecture, not only just use 3D. That's the reason of that is we actually try a lot as different architecture level, and the reason we combine this together is that we saw in this way the whole network, when you're doing the training, is give you the very good stability. I would like to see the sustainability of the whole network. So that's the reason we now use a single of the network. We use like 2 channels. We did meet the case, one channel is failed, but other channels perform good, but the overall performance is still good. So the whole network will, with your data you train, is give you very stable result.
So stable in terms of what?
Stable, the single one. For example, stable, then only you use a CN-RNN, or you only use a C3D.
Yeah. So what's your measure of this model being more stable than the other?
what I'm seeing is the overall performance is stable. See, it look like these algorithms because you know sometimes the neural network model is kind of sensitive to the sample data what you have. So with this a combination of those two channels together, so if you can get a very stable result, even though one channel is perform not good and the other channels still perform good. So we saw this could improve the whole performance of the algorithm.
I see. I see. My last question. What would be an application for this model? Like like you're telling me that within this 100 features of the network is going to be predicted in the next 5-10 minutes, 30 minutes. So
yeah, if for example there's because this type of data GPS based trajectories is gradually available everywhere. So for example, even in US, as my knowledge, the company like INREX, and they can roughly tell me they have in some urban area they have already have a 10% of a penetration of the GPS trajectory data, and they could be down the path could be a new data sources, for example, for track management center. So you measure especially for example for the large metropolitan area and the whole city, it gives you the macro level of the picture of the whole congestion for the whole city, because all the system traffic management systems have their own detection system as well, and then you can that portion of data to tell you what caused the problem. This can give you the view of the whole system-wide picture of the how congestion can be migrated.
I have to stop you here. Sorry for that, because we will restrict on time, and we have the third presenter from overseas. So if you don't mind, we can always discuss. Will be more time after the third presentation to go ahead and answer more questions. Thank you very much, Mr. Ken. And
thank you.
The third presenters will start accessing the presentation. So we're supposed to have Mr. Nguyen, right?
Morning, I'm here.
Good morning. Do you have a presentation to share with us?
Yes, sure. Can you hear me clear?
Yes, we can hear you.
So, on good. Yep.
So the last talk will be a deep learning system for travel speed prediction on multiple arterial road segments. And that will one of the seminar for today. So you can go ahead and you have 20 minutes.
Yep. Can you see my slides?
Yes, we can see your slide.
Yeah, so we can start now. So good morning from Sydney. So we are around 8 a.m. today. So thanks for your organization, and we are very happy to present our paper today. So I also have Dr. Chen Kai, our transport analytic research group leader. So he also a co-author. So would you like to say something to us?
I just give time to you and for time's sake, but it's nice to present our work here and to everyone. Oh, please continue.
Yep. So today we would like to present our paper, multivariate deep learning methods for short-term travel speed prediction. So this is the outcome of a research project funded by Transport New South Wales. And our presentation will be organized as follows. Just a very quick introduction and our motivation to conduct this research, and then very brief overview of deep learning, and then we will show our future generation of preparation. followed by the system architecture, along with the experiment results. The live demo, not really live demo of our visualization system, how it can be applied in the for processing the real-time data or to support real-time decision support for the transport management center. About our motivation to do this research. So we all know that being able to accurately predict the short-term travel speed. So in this case, up to half an hour is important for the public transport operation and planning, especially in resource and congestion management. In terms of incident processing, so it's also very useful. For example, we can do something like incident detection or anomaly detection to see the unusual traffic patterns in the road network. We can also use the model to predict the incident impact on the nearby road network. And the other application is some kind of predicting the recovery time of the traffic condition after the incident. For example, how long after the incident the traffic back to normal. So that's some of the application. So what is the key from the literature? So to the best of our knowledge, the majority of existing short-term travel speed prediction, they mainly focus on a single road segment, especially the motorway or highway. And by doing this, they solely capture the temporal patterns in a single time series or single time road segment and ignore the intercorrelation between traffic condition of the nearby road networks. And we also know that travel speed is not only affected by the temporal factors, but also heavily influenced by the other spatial related road segment nearby, like road segment congested. Here may lead to many other nearby roads also congested. And the other thing is our method can predict the travel speed simultaneously for several hundreds road segments in a small arterial network. For example, for corridor or for the whole suburb, and is able to be scaled in a bigger network. So in the current experiment, we have done the prediction for like more than approximately 300 road segments within the whole corridor. So let's talk about the deep learning. I think everyone here are very familiar with the deep learning network. So I just quickly go through it. So the difference between traditional neural network and deep learning network is the simple neural network basically just have one input layer, one hidden layer, and one output layer. In case it has more than one hidden layer, it's called a deep neural network. So it's just simple like that. And in this network, we have different layers with the nodes connected by the link. Each link may have a weight, and the model, the value of each node is computed based on the weight of the link and the previous value of the node in the previous layer. And the model fitting or training is the optimization process to decide the best weight for each link so that it can minimize the prediction errors. And we see that this is not a new method, but due to the recent development of the computational capability, for example, the GPU, the modern neural network may have like thousands of nodes and layers that make it more powerful than the traditional machine learning method. And why should we use deep learning? Because it can bring us the rate, power, and flexibility by trying to behave like a human brain. So the deep network learns to represent the words at the nested hierarchy of the concept, and the more complicated concept is defined by the similar concept. The same thing with the abstraction level. So the more abstract representation computed in terms of the less abstract one. And the key advantage over the traditional machine learning methods usually no or very less feature engineering or feature selection process, it requires the model can do all the generalization and also feature selection to decide the relevant feature for it to learn from. And it can learn the high level features from the data in an incremental manner. So in the simpler work, if we have the neural network with many nodes, many layers, it means it has a more different combination, so that it can learn more and more, like could be millions of different features in an efficient way. The only problem is the computational issue, but now it's no longer a big problem with the modern GPU. So we mentioned that the feature selection is almost no longer required, very little, but the other process like feature generation or presentation is still important, because the way we represent the data could support the model in learning the dependency, also the relevant feature. So for example, in this case, our data given the a small transportation network like this, the color-coded segment are the row with available Google travel speed. And we know that the travel speed come in the time series format, and we're gonna do the prediction for all the row segment within the area. It means for all the time series within the sub network. That is the reason why we call the method is like multivariate time series travel speed. The first thing to do, we need to convert this time series into the sequential feature matches. So at the sequential matches at time t minus I will contain all the travel speed of all the row segment at time t minus I. So delta is the look back window. For example, if we have delta equal to 10 and each time step is 5 minutes, so we basically use like 50 minutes historical data to make the prediction for the next step travel speed. And this next step could be from 5 minutes to half an hour. It depends on what we would like to predict, and then we just put into the training value for the model. So after we got the sequential matches, now it's bring into our deep learning architecture. So it's a combination of convolutional network or CNN, long short-term memory network or LSTM, and the dropout layer. The reason we use this combination is explained as below. So the convolutional network or CNN is very popular in the image processing, especially, for example, for 2D image. It can be designed to learn the relationship between the nearby pixels. That's the idea, that if we can represent the transport network similar to the 2D image, so the CNN can learn the spatial dependency between related row segments. So if we have the sequential matches, it can be considered as a 2D image. Or more generally, if we have tensor, it could be a higher dimensional image. So the same idea could be applied here. With the convolutional kernel, it can learn the nearby row segment relationship and then generalize and so on. So as our convolutional network is standard one with one convolutional layer and one max pooling layer. And then after that, we will fit it into the LSTM network. So LSTM is famous for capturing the long-term temporal dependency in the time series, because it has a very special internal structure that can control the weight and the volume of information flow. Basically, it's like can control which one to remember or which one to forget, so that's why it can get a longer and more relevant context around to learn the long-term dependency. And the very popular problem of deep learning network, because when it has too many nodes and layers, it may be prone to the overfitting problem. which means it performs very well on the trained data, but quite poor on the test set. And our layer in this case to reduce the overfitting problem. So dropout layer basically randomly drop a certain of nodes in order to increase the generalization of the process. So in this case, we use the threshold around 50% of the drop node, and it followed by the dense layer to control the number of the output, usually equal to the number of row segment we would like to make a prediction. That the back-end deep learning architecture. When it's coming to the real-life application, this is our general system architecture. With the best model come from the experiment, we can store it in the database and then use for real-time prediction. So how it's gonna do? Real-time travel speed may come in the time series exactly the same time series format. That's why we need to apply the same feature generation so that the model can perform at its best performance. And this after this process, the input can be stored in the historical data. After we have sufficient new data coming, or after, if there is major change in the traffic system, or after like 3 months, we would like to update the model, we can use this data to retrain the model. And this is the iterative process. So the model training is very fast. We can do it like once a week or even daily. And real-time prediction result can be done in like milliseconds for at least 300 row segment, and the result can be displayed in our visualization system, which have been well received by the transport New South Wales. And some of the experiment results. So I saw the result for single segment regression and also the overall root mean square error. For the we put the row segment 8474 with the train data is the orange one. The test data is the prediction data is the green one, and the blue one is the gold standard. We can see that the prediction it fit quite well with within the route choose. That's for the single one, and for the whole corridor, we use the root mean square error. So in most cases, the system perform much better than the traditional machine learning method, especially from 5 minutes to 20 minutes. And for the longer one, it's so a drop for like up to half an hour, but the system can have a special switch to the special LSTM network to make it perform the best on the half an hour prediction, because LSTM, the longer ones, longer prediction, it usually show the advantage for the learning the long-term dependency. So some more detail you can find it in our paper. And now I can show you our visualization system. Can you see the browser?
Yeah, we can see it.
That's good. So I can go ahead. So this is the investigate Victoria corridor in New South Wales, Australia. So we have the time slider to choose the time we would like to investigate. So I choose like 10 of the April 2017 data, and then I would like to load the traffic condition. So it will show on the left is the real historical data, and on the right side is the prediction data. And we can choose from 5 minutes to like up to half an hour prediction to investigate. So if I zoom out, we can see the whole Victoria corridor. So it contains around 300 row segments as discussed. So I'm gonna pick the 474. Before when we click in on a row segment, it will show the prediction, the real-time data and the prediction. We can see that for 5 minutes, it fits quite well. So just make it harder by look at the half an hour data. So I will show one example for the normal day prediction and one example in case of the incident. So we can see some real application of the system. We can see here for a normal day. For standard rush hour in a normal day. So if this is even for half an hour prediction, the model perform pretty well. On the left side is the plot of the time series, and on the right side is like half an hour prediction. So this is 5 minutes prediction. This is 10 minutes up to half an hour as compared with the gold standard. So we can see that for a normal day, the model perform pretty well in capturing the traffic pattern, and even half an hour prediction is quite very close with the real traffic data. That is for the standard traffic condition. Now we will look at the harder case in case of the accident. Let's move to one day ahead. We have today. So on the next day, we have the traffic accident around 9:40 happened around 9:45. Earlier, because it's report 9:45, it could happen around 9:30. So we can see that there is a big gap here. So it's very normal. The model couldn't predict the accident like happened an hour ago. It can predict it very weird, very unusual for the model to predict. But what we can learn from here is when there is a big gap between the prediction and the real-time data that we receive incrementally, we can say that could be something unusual in the traffic pattern. So it can be used for the incident detection or anomaly detection. So that's one other application of the model. The other thing is the model couldn't predict the incident, but when it started to learn the unusual traffic pattern, slow pattern here, we can see that the recovery time, it can predict how long after the incident the traffic condition come back to normal. So that's another application for incident duration and traffic condition prediction we can use from the current model. We see that from here there's a big gap, but this gap closing very well later when the model learn the slow traffic pattern. So that's the demo of our system. We come back to the slide. So that pretty much, so to sum up, so I propose a deep learning architecture with a combination of CNN and LSTM, and along with the dropout layer to capture the temporal and spatial dependency between multiple row segment travel speed. And our system is quite flexible and is able to train multiple deep learning models like CNN and LSTM or just LSTM. And we can see that the deep learning model perform the best in most of the tests, and our proposed model can be deployed in the real time and provide a forecast of short-term travel speed for the whole area or the whole corridor. So from the demo, we can see that if we fit in the real-time data, the model can make a prediction and display the result very similar to the system, and so it can be useful for the transport management center to support them for incident processing or just normal daily traffic monitoring. So that's the end of our presentation. Thank you. And if you have any questions, so we are happy to discuss.
Thank you very much. Thank you very much. This is, of course, the last talk today. So any question from the audience?
I have a question. This is Osama.
Yep.
So this is a very interesting presentation. So thank you for that. In the app that you're trying to show, I'm not sure actually what were you showing us, because this is pretty much a snapshot from the app, not the app itself.
Yeah, I can pop it up. No worry. Let me choose.
Yeah, when you click on this link, I mean, like nothing changes. Yeah, so you're okay. So this was not showing at all during the presentation.
Oh, it's not showing?
Yeah, it was not showing at all during the presentation. I didn't
very
want
sorry.
to.
Yeah, because I just anyone can see my browser, so it's not showing.
So I mean, yeah, if you can briefly talk about it again, please, that would be great.
Yeah. So very good. So basically, we can choose the time like between 5 minutes or half an hour prediction, and this is on the left side. We know that this is the real time traffic, and this is on the right side is the prediction. It's also got the color coded. So when we click on the one row segment, here we can see the time series along with the prediction. Here, so I'm gonna show one normal case, normal daily traffic pattern, and one case for the incident. So this is the normal day, normal traffic, the morning rush hour. We can see that even with half an hour, the model can perform really well. And when I play it, this is similar to when we have the real-time data, how the system perform and display the result. So it's running even half an hour, the prediction is very close to the real-time data. We can see that this is the standard rush hour, and the harder case is for when the incident happened. So we got on the next day, morning rush hour of the next day. There was the accident around 9:30, so it's within the morning rush hour. So for half an hour prediction, we can see there is a big gap here. So of course, as I mentioned before, it's very unusual for the model to be able to predict the accident like half an hour ago. So in its view, the model thinks that the traffic condition will back to normal very softly like after 9:30, but because the incident is a slow traffic pattern here, so the application we can use here is like anomaly detection or incident detection when we see the big gap here, so to detect the unusual traffic pattern. So that's one application. The other application is the model couldn't predict the incident, but when it learned the slow traffic pattern here, even if very unusual, the model is to be able to predict like when the traffic back to normal, like could be incident duration, and when the incident clear up and the traffic condition back to normal. So on the right side, we can see this day up to half an hour prediction here. Initially, the gap is very big because the model didn't know the incident, but when it started to learn the incident, we can see that it can predict the recovery time very well, even half an hour ahead.
Amazing. So I have a couple of questions about this amazing visualization tool. So when you move this time slider, does it recalculate the predictions, or is it already calculated, or like the predictions are already made and they are stored in the let us say in the back end or whatever? Just calls them to show them.
Yeah, that's a good question. This is just the demo. So it's not a real time at this time. So we just load the prediction and the historical data. So it doesn't make any real time prediction. But what we mentioned is it is able to be deployed in the real time.
So all these predictions are already calculated. You're just visualizing.
Yes, that's correct.
Got it.
Just
Got it.
visualize the concept to be able to use.
I see, I understand. So is there a real-time component here in this tool?
Sorry?
Is
Can
there
you
any real-time component, like at least like visualizing real-time conditions, that kind of thing? Do you have?
No, not in this one. It's just historical data of the
Okay.
data we got. We got the time here, so it's historical data. But we are working on deploying the real-time prediction with the traffic condition.
Okay. So what tool did you use to develop this?
This is the Shiny on R. So this is the visualization supported in R. It's called Shiny. So it's very easy. So there's no JavaScript at all. So basically we just written in using the R language, and then it will have some built-in tool to convert into JavaScript and be able to display. So actually we deploy this on the Amazon server. Yep.
Okay. Is it Sign E?
Sorry, Shiny. Yeah. Shiny. Yeah, like the sunshine. This is Shiny. I can show you the link here. Like to know.
Yeah, please. Yeah. Shiny. Okay. Okay.
Yeah.
I see. All right.
This is a very good tool because it's very close between the data scientist and the visualization. So it's the tool for the data scientist to do the visualization. Don't need the engineer, software engineer, and it's very good to deploy, visualize the chart in real-time data like this.
Perfect. Perfect. Yeah. Thank you very much. Thank you. Amazing presentation. Thank you.
Hello,
Thank
I
you.
have a quick question. This is Ulash from UCF.
Yep.
Thank you for this promising work. I have actually one small correction and one quick question.
Yep.
Correction, actually, it is not really standard in computer vision and machine learning language to call a network multivariate network based on just input. Your input can be anything with LSTM, and you don't really call it like multivariate. This is just as, the suggestion to correct. I have a question in terms of dropout. Your dropout use is not really the standard. So usually you use dropout in layers to select the neurons randomly, and you repeat this many times to improve the generalization. The way you use dropout, it looks to me like you have a bunch of features and you rank them, and then you select some of them to proceed. This is actually what I guess from your presentation. Is that right?
Not really. So it's just a last step, the feature. So just fit in like naturally. We didn't need to run or do anything. Just the last step before the final output. So we do. Actually, it's not a single dropout. We run this experiment for around 10 times and get the average, because there's always some fluctuation. That's why we run 10 times and
Sure, but at the end you have lots of features, and some of them are actually pretty good, useful features. How did you select them to remove from your system? Is it random?
Yeah, it's just random. It's just a random single factor in the dropout layer. Like
Maybe,
single.
I see. Yeah, thank you. Maybe that may be the reason that sometimes, especially in this demo, you show the real trajectory and your prediction. Sometimes it is really diverging. It may be highly likely because some of the useful features you are really get rid of. If you do the dropout throughout the network, you can. I think this is a good study, and you can further improve the system.
Yep.
Otherwise, because of there is a large gap between your prediction and your real trajectory from time to time. And you can, just as a small suggestion from, again, machine learning perspective, you can look at the confidence interval of your prediction to see where you are really removing those, the good features. Otherwise, I think it is a good study. Thank you.
Yeah, I think a good suggestion. That's correct. So something further work we can do this. Investigate the dropout. To choose the good one to remove. The good one in terms of it's not quite useful, so we can remove. That's a good suggestion. We can investigate further. Thanks for that. Yeah, any other question?
I think we are already running out of time. I wish we can ask questions. I mean, I will be here for some time. It will be open maybe for 10 more minutes for the different presenters. If anybody would like to ask additional questions. And otherwise, thank you all for coming, and we hope you enjoy this variety and impressive work that it's been in the committee. We've been seeing more and more of those excellent work, and I hopefully next year we'll also be able to get exposed of novel ideas. And thank you for everybody for presenting and for attending. As I said, I will be here, and some presenters, if they wish to be here to answer more questions, that would be good.
Mohammed, I'm sorry, I have one question to all presenters. Are you all going to be attending the upcoming TRB or
Yes, we are attending. The UCF team will be at the 2019-20 TRB.
Perfect. All right.
Yeah.
And also, I would like to have a special thanks to Dr. Osman, who basically allow us to use this service Zoom for presentation, and actually he's part of the committee, selection committee, along with Dr. Mehdi and Dr. Khan Albay. Dr. Mehdi is from UT and Dr. Khan is from New York University. I'd like to thank them all because they are basically the one who made this happen. And of course, the ABG community as in general for the reviewing and filtering all the good papers so we can come up with this interesting set of three papers. Thank you all.
Thank you. Thank you. Bye.
Thank you, Dr. Zaki.
Thank you very much.
Thank you.
Thank you.